So in this lesson, we're going to start with some opening problems to review a little bit about what we've been doing, but then we're going to go ahead and talk about a new subject which is called logarithms, which is the inverse of the exponentials we've been working with. So the first thing I'd like you to do is, if you have that downloaded PDF, if you could take and try these opening problems. Pause the video, just try those problems, and then come back to the video when you're done. So what I'd like to do is, I'm going to, first of all, say that our objective here is I can convert exponentials into logarithms. Now, the first thing we want to do is let's review a couple problems. So hopefully you've tried this problem. This is the depreciation problem that we've been working with. And the formula we use is that A of t equals, when it's depreciation, we have the initial amount, which we call A, times 1 minus r to the t power. Now, the A in this case is our 27,000, so we're going to do 27,000 times 1 minus, and the rate here is 9%. Well, that's what we're going to list as 0.09 to the t power, which gives us a formula of 27,000 times 1 minus 0.09 is 0.91. Because that's between 0 and 1, that's a depreciation problem, to the t power. Now the next thing we want to do is go ahead and put in, into this problem, the time that's listed there. So if we take and we put in, we do A, in this case, of 3, that means we're going to have 27,000 times 0.91 to the third power. And then we just do that on our calculator, and that equals $20,346.42 is our answer. So that's how we do a depreciation problem. All right, so let's go ahead and take a look at these. And again, you can pause at any time if you want to write that down, if you want to take some notes. So let's go ahead and solve for these problems. Solving for x on this one, reminders when we're solving an exponential, the goal is to get the two sides to have the same base. So 8 and 32, 8 to a power doesn't become 32. So what we want to do is maybe go up for a lower base. Well, 2 goes into 8 and 2 goes into 32. So when I do this, I set it up as 2 to the third, because that's 8 to the x plus 2 power, equals, now 32, that's equal to, in this case, 2 to the 5th power. If you multiply 2 out 5 times, you get 32, and that's to the x power. Let's go ahead and multiply our exponents. So 2 to the 3x plus 6 equals 2 to the 5x. Once you get them with the same base on both sides, you can set the exponents equal. So 3x plus 6 equals 5x. Subtract 3x from both sides, you get 6 equal to 2x. Divide by 2, you get x equal to 3. So that's how you solve an exponential. Let's talk about graphing. So looking at this one, what I'm actually going to do is I'm going to do it this way, and then I'm going to talk about what would happen if we added a number onto it as well. So I'm going to start with, let's graph this one. I'm going to set up a table. You get this table from your graphing calculator. And the numbers I got off my graphing calculator are -2 gives me 0.06, -1 gives me 0.17, 0 gives me 0.5, 1 gives me 1.5, and 2 gives me 4.5. So let's go ahead and draw a graph. So again, I'm going to do a sketch up here. I'm going to draw my axes. Let's do that in black here. So if I draw my x-axis here, and then I'm going to draw my y-axis right here. Okay. Now when I graph these points, notice that these are very tiny. They're going to be near the x-axis because the x-axis is the asymptote. So when I graph negative 2.06, that's really close to the axis. Doesn't get there, but it gets close. Don't cross that axis. Negative 1, I go up to 0.17, which is very close still. 0, I go to 0.5. And then at 1, I go to 1.5. And then at 2, I go to 4.5. So up 1, 2, 3, 4.5. Draw my graph. And then it accelerates up. So asymptote is the x-axis. We don't cross it. We get very close to it. And then my graph is an exponential growth problem because my value 3 is larger than 1, grows exponentially. Now what would happen is if I took this and I instead added a 10 to this, well, all of these numbers then would have a 10 added onto it. So this would become 10.06, this would become 10.17, this would become 10.5, this would become 11.5, this would become 14.5. And so all these values would be up 10 units. So now we would have a new asymptote at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It would be right here at 10, where my graph would get very close to that asymptote. It would cross here. It would go up to, at 1, I'm at 11.5. So I'd go up here to 11.5. And then at 2, I'd be at 14.5. So 12, 13, 14.5. And so it would go up like this. So notice adding a number at the end moves the asymptote up. I got to draw a dotted line to show that that's been moved up. If that had been subtracting a number, it would move it down, and that's where my dotted line would be. So something a little extra onto that problem. Now, let's go ahead and actually define logarithms. That's where our goal is. That's all review of exponentials. Let's move on to a new topic, which is called logarithms. Okay? So an introduction to logarithms in exponential form. The key idea here is that a logarithm is the inverse of an exponential. Whatever the logarithm or the exponential does, the logarithm will undo it. Now, it won't be quite as obvious about that fact until later as we work more with these problems. But for now, what you need to realize is that if we have an exponential, b, let's say b to the y equals the number x, okay, if that's our exponential, then what we have when we do this is that the logarithm problem of it is set up as log with base b down here. Just that's a subscript, it's below the log, just like an exponent is a superscript above. This is below, down lower, and then log base b of x is going to equal y. So what you have is this is the base, and then notice that the exponent is what we're finding as the answer to the logarithm. Here we put the exponent in, there we get the exponent out. That's why they're inverses of each other. So what we have is we call this is called the base, log base b of x, and this is the exponent is the answer. notice I'm going to refer back to that exponent up there. It's the answer to the logarithm problem. So simply put today, all you're going to do is you're going to convert. You're going to take these logarithms, and we're going to logarithms, convert them to exponentials, and these exponents, and convert them to logs. So on this, when we want to write this as an exponent, this is the base, the subscript, so 3 is the base. That number is the exponent, so we put it up as the exponent. And that number is the answer to the problem. So we just convert by taking base to the exponent equals the answer. So as we do that, let's convert this one. 10 is the base. The exponent is 2 equals 100. That's converting that log back into the exponential form that we're more familiar with. And this one, as we convert these, we're going to take this and we're going to say, okay, what's the base? Well, the base of this is base 5. You're going to take it of the 625. That answer goes on the inside of it. And that's going to equal the exponent. The exponent's the final answer to the log. So 5 to the 4th equals 625 is how we write that. And this last one, the base just happens to be, in this case, a 1/2 or 0.5. The number that is the answer to this problem goes on the inside of that logarithm. So log 1/2, base 1/2 of 1/8 is going to equal the exponent 3. And so that's how we do the conversions to logarithms.